Thank you, Professor Paolone, for introducing me. The title of the paper I'm going to present is Chattering-Free Modeling and Simulation of Power Systems with Inclusion of Filippov Theory. And my co-author is Professor Federico Milano, who is my supervisor too. In this presentation, I will first formulate the research problem, then I will show how Filippov theory is applied to solve the problem through two case studies. Electromechanical dynamics of power systems are conveniently modeled through a phasor-based model. The phasor-based models are described by a set of discontinuous nonlinear stiff differential algebraic equations. And those DAEs during numerical simulation subjected to a disturbance shows chattering genotype deadlock issue. This phenomena is often observed in anti-wind-up proportional and integral controllers modeled according to the IEEE standard 421.5 2016. This paper designs a general purpose model of the IEEE standard 421.5 2016 anti-wind-up PI controller based on Filippov theory. And the proposed approach allows numerical integration along the deadlock region, and it removes the chattering and other numerical issues. IEEE standard recommends a conditional type anti-wind-up PI controller model to avoid the wind-up effect. The conditional integrator sets the input to the integrator 0 when the control output is beyond its limit. This figure shows the state transition of the anti-wind-up PI controller model. Observe that this anti-wind-up PI controller model has three states: the integration state, the maximum state, and the minimum state. Now, during the numerical simulation, this model shows deadlock issue. Now, what the deadlock means? The deadlock means indefinite switching between discrete states within a time step, and that halts the simulation. That means the simulation cannot continue anymore. Let us consider at time t1 for an input ut1, we go from the integration state to the maximum state. Now, to move back from the integration state to the maximum, from the maximum state, again, for an input ut2, at time t2, all these three conditions has to be satisfied, considering depending on the different numerical methods. Otherwise, a deadlock situation appears. I also observed that for a simulation step or the interval h equals to 0, their deadlock doesn't appear. Now, there exist several techniques to avoid or to solve this issue. The first solution is using a deadband. This technique modifies the state transition diagram. It introduces a deadband here. Now, to move from integration state to the maximum state, the controller output has to be greater than the maximum value. However, to come back from the maximum state to the integration state, we need the controller output has to be lower than the maximum and also the deadband value. The second method is a time delay method. This method to move from one state to another state considers the integrator state variable magnitude from the previous time step. And the third method is a no convergence method. So a software tool can introduce a no convergence method. This solution forces the solver to move to the next time step after certain number of iterations, even if the solver doesn't continue or the solver doesn't converge. And the final method is the semi-implicit method. The semi-implicit method converts the integrator state variable to an algebraic variable to continue the simulation when the deadlock situation appears. The drawback of these first three methods is that they introduce artificial chattering. On the other hand, the semi-implicit method requires a solver-dependent implementation, which is not supported by most power system software tools. So considering these drawbacks, we propose a Filippov theory-based design to overcome the difficulties or the drawbacks of all of these methods. Now I explain briefly the Filippov theory. The Filippov systems are dynamical systems with discontinuous right-hand side first-order differential equation. Let's consider these Swiss dynamical systems with the vector field F1 in the region R1 and the vector field R2 in the region R2 in the state space. And both regions are separated by a switching surface sigma. Now, Filippov convex method states that the vector field on the surface of the discontinuity is a convex combination of the vector fields in the different regions of the state space. Let's consider a trajectory. It starts from here at time t0 with an initial condition x0, and it reaches to the switching surface at any finite time. Now, if the trajectory moves near to the switching surface, Filippov first order theory explains what to do. Should we cross, we come back, or we stay here? Now, if we cross or come back, this is known as a transversal crossing. And the transversal crossing happens if this condition becomes true. Now, check other two conditions. If this condition is true, the trajectory will move from this region to the other region. And if the other condition is true, the trajectory has to come back to this region again. Next, if this condition becomes true, there is a sliding condition appears. And the sliding can be an attractive one and a repulsive one. For the repulsive sliding, there is no guarantee of uniqueness, so we do not consider the repulsive sliding, and which is not relevant for our work also. And the attractive sliding will happen if both of these conditions is true, and during the attractive sliding, and the solution will stay in the switching surface. And during the sliding, the vector field is given by the Filippov formulation, and this is given by this equation. Now, during the sliding, if one of these vector fields starts to point away, now the solution will continue above or below the switching surface. So I explained the Filippov theory. Now I will design the anti-wind-up PI controller based on the Filippov formulation. And this is my anti-wind-up PI controller. And to design it, we represent the dynamical system according to the Filippov theory. And conditions to check when the trajectory when the trajectory reaches to the switching surface are derived here, and the sliding condition is also derived here. Now, based on the Filippov theory, the controller has three states: the integration state, the maximum state, and the sliding state. So for the implementation, we introduced two different discrete variables, the Z1 and Z2. And we show in this figure the changes in Z1 and Z2 in different sliding state. And we also show the conditions to move from one state to another state. Note that all of these conditions are derived using the Filippov formulation. In addition, following a similar procedure, a complete state transition scheme can be obtained to consider the lower limit also. Now, I show the problem. Now I explained how I solved the problem using the Filippov theory by briefly introducing the Filippov theory. Now I validate my method using the case studies. The first case study I consider is a single machine infinite bus system. The generator model here is a third order type, and it is equipped with a ST4C type excitation system. The excitation system, all of this PI controller and the lag block is an anti-wind-up type. And we also have a PSS in the generator. The first contingency, we consider a three-phase fault occurred at 5 seconds and cleared after 100 milliseconds. Following the disturbance, both PI controllers and the lag block in the AVR reaches their limit. This figure shows the time derivative of the integrator state variable with respect to the integrator state variable in one of the PI controller. And also, this figure shows the trajectory for the Filippov theory-based solution, the time delay-based solution, and the deadband-based solution. So we can observe that the Filippov theory-based anti-wind-up controller provides a smooth response compared to other two methods. The main advantage of our Filippov theory-based formulations are that it removes the artificial chattering, and compared to other methods, it requires less state events and thus less computational demanding during the deadlock regime. Next, I simulate the same single machine infinite bus system again by perturbing the voltage reference set point and the load set point. This one I show again just to validate my model again. So for the following the contingency, the controller moves from the integration state to the sliding state, and from the sliding state to the maximum state, and from the maximum to the sliding state again. Now we intentionally perturb the system again here so that the controller moves from the sliding to the maximum state again, and it comes back to the integration state through a sliding state. And in this figure, we show the output of one of the PI controller with respect to the integrator state variable. So, and these results actually proves that the proposed model is consistent with the other implementation, and it captures the hybrid dynamics without creating any chattering or artificial chattering. Note that the number of switchings, while considering the deadband and the time delay based method depends on the deadband width and also the time step of the simulation interval. And this indicates that chattering is a simulation issue, is not a physical behavior of the converter. And in these simulations, we use an event-driven method. That means we calculate the switching surface through not by an interpolation, like a accurate switching surface. We calculate the accurate switching surface. The second case study, we consider a voltage source converter based flexible AC transmission device, namely STATCOM, in the WSCC9 bus system. And to model the STATCOM, an average value model of the converter is considered, and a vector current control based on DQ composition with the grid phase voltage as phase reference is used. The converter and its control loops are shown in this figure. The DQ components in the outer control are utilized to control the DC and the AC voltage respectively, and all the controllers inside the outer control loop and the inner control loop are anti-wind-up type PI controller. Now, in this figure, we apply the contingency, a three-phase fault at time 1 second, and we apply it for 60 milliseconds. And we clear the fault through disconnecting the line in between buses 6 and 9. The lines are reconnected at time 6 seconds. In this figure, we show the response of the output of the AC voltage controller in the outer loop. And in this figure, we show the time derivative of the integrator state variable with respect to the state variable of the AC voltage controller in the outer loop. So similar to the previous case study, the controller with the Filippov theory achieves a smoother transient response. Also, at time 25 seconds, we apply a step decrease in the reactive power load. And following this disturbance, the controller moves to the lower limit. Observe that the proposed method also provides accurate transient response without any numerical chattering. And in this method, we simulate using a time step technique. So the conclusions are, a general purpose state transition diagram is proposed to model and implement the IEEE standard 421.5 2016 anti-wind-up PI controller. The proposed model is based on Filippov theory, and it removes the trajectory deadlock and also the chattering. The case studies show that the proposed design provides accurate dynamic response and suitable for implementation in a power system software tool. And in future work, we'll extend the Filippov theory-based anti-wind-up PI controller to impose time-varying limits. Thank you for listening. If
Thank
you
you,
have any
Mohammed,
questions.
for the presentation. So we have time for one quick question that has been already posed by Andrei Gorbunov. So he's essentially asking whether the chattering phenomenon is occurring in simulations only, or whether it can actually take place in experimental implementation, real implementation of digital controllers.
So we did not do the real implementation, but from our study, we concluded that this is a phenomena of the simulation. It is not a phenomena for the physical.
But can, in your opinion, take place also in a digital controller as well?
Okay. If it's a digital controller, it can happen if someone consider anti-wind-up PI controller based on the conditional integration and the IEEE standard one. This
Okay.
one, it can happen in the digital control. Yeah.
Okay, good. Thank you very much, Mohammed, for the presentation and this very efficient reply.